Hello students, welcome back. Let us resume our discussion in section 4. We want to establish and prove the multiplicative property, and we have two proofs here. Let's do both. And our textbook's method is proof 2, but frankly I found it very hard to follow, and I don't know how to explain that either. Let's do proof 1 first. The proof using the Chinese remainder theorem. Here's the setup. Define the sets A, B, and C like this. Positive integers not exceeding m that are relatively prime to m. That's A. Positive integers not exceeding n that are relatively prime to n. And finally, positive integers not exceeding m times n that are relatively prime to m times n. Needless to say, the number of elements of A is phi of m, the number of elements of B is phi of n, and the number of elements of C is phi of m times n. Clear from the definition of Euler-Torsion function, isn't it the case? Yeah. Now we aim to prove the Cartesian product A times B has the same number of elements as C by constructing a bijection. How do you construct a bijection? Well, we're going to use the Chinese remainder theorem. X is congruent to I mod m. Given I comma j in A cross B, so I comes from A, J comes from B, yes. We have I and J as arbitrary elements suggested in here. And I'm going to use C for K, or K for C. All right. X is congruent to I mod m, and X is congruent to J mod n. There goes the system, and m and n are relatively prime, so we can apply Chinese remainder theorem so that there is a unique solution K modulo m times n. And define a map f of I comma j is K. There you go. Then by the Chinese remainder theorem, this is a well-defined one-to-one onto map. So this must complete the proof. Or does it? Oh, I have a bad feeling about this. Or does it? Probably not. Why not? What fails? Think about that. I mean, we have a congruence here, linear congruent, a system of linear congruence, and that unique solution. Unique solution, so the map is well defined. And then uniquely determined, so 1-to-1. Now, is it 1-to? Well, onto is not a problem either. So arbitrary K, just put K there, then X is congruent to K, and then that's congruent to a certain I. X is just K, and that's congruent to certain J. You see, K goes from 1 through m times n, or actually more precisely speaking, 0 to mn minus 1, because we are doing modular mn. And then m and n are smaller, so by division algorithm, you'll have to bring K down further to I. So no problem here, as a matter of fact. If you simply begin X is equal to K, then put those in, I'm going to get appropriate I and J. That's where we're going to start and end up back here. So yeah, we have one-to-one onto bijection. No problem. It's well defined. But why does it not complete the proof? Well, here's the reason. Not so fast. The map F constructed like this was defined for all ij where I is greater than or equal to 0 and less than m, and j is greater than or equal to 0 and less than n, and for k greater than or equal to 0 and less than m times n. You see, we are using mod m and mod n and mod m times n. And those are for Zm, Zn, and Zmn. I going from 0 to n minus 1, j going from 0 to n minus 1, k going from 0 to mn minus 1. And we just defined a map on one-to-one onto bijection from Zm cross Zn onto Zmn through this Chinese remainder theorem. How many elements are there here? M. And how many elements are there? N. How many elements are there? M times n. So Cartesian product, we just proved Mn is equal to Mn. That's what we did. Mn is equal to Mn. That's what you proved, as a matter of fact. It's not really a proof we want. We got the correct map, yes, but if we do not restrict the domain, we just end up with m times n is equal to m times n. We have to restrict it further. What we want is, this is correct map, but restrict it down to A cross B. Then does it map onto C? One-to-one and onto is, of course, always the case because this one is bijection. So does this map onto C and vice versa? That's the question. All right. This is map, this Chinese remainder theorem, and the unique solution is defined for everything from 0 to m minus 1, 0 to n minus 1, onto 0 to mn minus 1. Relatively prime thingies, these parts, those are not considered here. So what we are going to do is to restrict it. If I and j come from A and B respectively, not just Zm and Zn respectively, just A and B respectively, then K comes from C as well. That's what you have to prove. Make sense? Just having this map using Chinese remainder theorem is not sufficient. They're too big. We have to restrict the domain into A cross B. Then what's the range? It'll be C. That's what you have to prove. In other words, if I comma j come from A times B, in other words, I comes from A and j comes from B, then K comes from C, and vice versa. That's what you have to do. All right. Then we have to go back a little bit further to Chinese remainder theorem, because having a unique solution like this didn't really have anything more than just this part. So going back to Chinese remainder theorem, and let's get the expression of K, the solution. So what is Chinese remainder theorem? Let me give you a brief reminder. So Chinese remainder theorem, and the unique solution looks like this. A1 capital M1 mu1 plus A2 capital M2 mu2, like that. And then capital M, those are the product of everything divided by M1 divided by the M2, like that. And then mu and mu2, those are their multiplicative inverses. So let's set up like that. Congruent to I, congruent to j, okay. So I and j, no problem. Instead of capital M, you could do m times n divided by m, and then here, product divided by n. That's how you got capital M1 and capital M2, right? But m and m cancel each other out, we just get n. And here, n cancel out, we just get m. And then nu and mu respectively are their multiplicative inverses. So we have this expression by the Chinese remainder theorem. From this point on, it's not too bad. Express this Chinese remainder theorem modulo mn as a solution of a Diophantine equation. So same as A and V, in nu plus j in mu, so far so good, plus an integer times qmn, q for a quotient, qmn. Here, modulo mn, here just equality thanks to this qmn. Make sense? So whenever you get this congruence down to the Diophantine equation, an integer times modulus comes out, and this mn is the modulus, so q times mn. Now here, apply mod m operation. Mod m operation will make all these 0, so what you'll get? Oh, mod m operation, n times nu is also equal to 1, mod m, so we get k is congruent to I. So k and I are the same as far as mod m is concerned. So we get this conclusion. GCD of IM is 1 if and only if GCD of KM is 1. You see, I and K are the same as far as mod M is concerned. So that conclusion is carried over to GCD. Exactly the same thing for J. So the greatest common divisor, I and M, carried over to K and M. Similarly, J and N carried over to K and M. Now, how will that help? It'll help like this. What do you mean? I comma J come from A cross B. That means I belongs to capital A and J belongs to capital B. So by this condition, GCD of I and M is 1. GCD Jn is 1. Yeah, all right. GCD Im is 1 and Jn is 1. That's the definition. All right. And then let us apply what we did using the Chinese remainder theorem. Replace Im to Km, as you saw here, and replace this Jn to Kn, as you see it here. Those came from Chinese remainder theorem. This came from the definition. The next line came from the Chinese remainder theorem. Now, putting these two together, we can conclude GCD of K, m times n is 1, and that came from this one here, which I highlighted before and spent a bit more time in the previous video, remember? Change of characters, instead of A, B, C, we have IJK, no, KMN, that's all there is. So we can reduce it like this, and now it's clear. That's the same as K belongs to C. So conclusion, I comma J belong to A cross B if and only if K belongs to C, and that association is 1 to n and on to bijection. Everything is done. And that completes the proof, by the way, finally. We have a well-defined bijection, so number of elements must be the same. So phi of m times phi of n is phi of mn. Let's open that again. So this series of computation directed from the definition, from the Chinese remainder theorem, from the lemma that we had before. Where is it? Where is it? Yeah, this one highlighted in blue. And the conclusion. Yes, tricky, I agree, but in the end we got it done. The Euler-Phi function is multiplicative indeed. We use the blue lemma here and the Chinese remainder theorem as the main tools.